All right, I am back working on Stanley, my Atari 2600 emulator. Uh, for those of you, a few of you who may have caught my partial streams before, was not feeling great on Friday, but I am feeling better now. And I think that I'll be able to make some progress on this. I want to go over sort of what we did last time. So let's take a look at our Git log. So we added some flags, a couple of instructions, and actually the important part here is there's some refactoring going on, and oh, interesting. Okay, I'm just looking at my. Okay, so I pulled that work in progress branch in, so I just get rid of it. If I can spell it right. I did not spell it right again. Okay, it's going off to a good start. It's been a couple days since I was at my keyboard. Clear. Okay. All right, so let's take a look at the code. So one of the main things I did is I pulled all these instructions out into individual little structs. There's no sort of data there, but there's this trait instruction. I'm going to switch around how this works. I think I'm going to save that for another day unless something comes up. But basically all the instructions have their code and like what it means to execute it given a mutable chip. So if I go to the main here, you can take a look at that big old loop, that big old match statement. This is a little bit more readable. I do think that I want to have something more like chip.execute. That takes a right, and then it'll pass itself in, because I do think that even this idea of the chip is wrong. So let me take a look at the chip file. Right now I've got things that are like a part of the 6502 chip, like sitting here on this NMOS 6502 struct, which is like the X register, A register. There's going to be a Y register eventually, program counter, stack pointer, some flags. That all makes sense, right? But then there's this like memory map, which is not part of the chip. The chip itself, the details of this are going to escape me a little bit because I don't know it super well, but just is connected to has a 16-bit address bus, so it's connected to memory. So like logically, it like doesn't own one; it just is connected to one, and that comes into play. How did I do that? Just actually bump this font up again. I keep hitting something accidentally that changes my font back to the standard, which is a little too small for stream. That's what's going on here. So the thing that gets me about that is that eventually the memory map here is attached to this TIA hardware and this Riot hardware, and it's attached to the memory, and it's attached, like, it's got the program memory and stuff like that. And that's not actually logically kind of how it works, right? Like, these things are all sort of on the board and they're connected via like wires, and then there's like some amount of control. Well, I think it is like a little bit how it works, but there's some control that goes between the TIA and Riot. Like there's some shared stuff. This is like getting into electrical engineering, and I don't fully understand it. And then the TIA actually even stops the 6502 from executing for a while. So that's what I'm looking at. But what I did in the meantime is I went through and did some stuff to make our execution a little bit more realistic. I was, and I still am, sort of returning 0 in all cases. The problem is that some of the defaults are not 0, right? So some of the default states are 1, for instance. This is the timer. We'll go up here. It's actually this 1 bit at the top of the byte that you read for the player 0 controller. And if this bit is set, the button on the controller isn't pressed. If it's unset, it is pressed. So returning 0 made it seem like the button was pressed, and it actually skipped a bunch of execution in our program. So for now, I'm just saying, let's just return the default state, so we don't have to implement it, but also we don't like go off on a wild tangent. The other thing is that we haven't implemented, the Riot chip has internal timers. We haven't implemented those timers, and so this was also returning 0, and it didn't necessarily need, and it wouldn't in normal execution because it's not actually counting down. So I'll show you where that is in the program. Let's see. Not streams. Tic-tac-toe. I went too far. Source. We'll go to intro.dazzle and I'll show you what I'm talking about. So that is this check right here in the kernel. We're basically waiting for when it's 0, I'm trying to remember. I think this is basically letting some stay on intro. Yeah, okay. Sorry, getting my bearings a little bit. So we're actually getting stuck in this loop here. And we're skipping over this whole thing here. That's why we're not getting stuck in this loop. So it's basically just like waiting for this timer before changing screens. Boy, I don't remember this. I wrote this years ago, so I don't remember exactly what's going on here. But basically, if I run this program now, it gets stuck in an infinite loop, which is kind of what we want, right? Because we want to have to we want that driver to or this loop to drive us, to drive out functionality. Hold on while I get my tongue in line here. Turn down this music. But we want this loop to stay here so that we can drive out the new functionality, which is what we're going to work on today, which is timing. So there's a couple things. Let's open a scratch buffer. All right, there's a couple things we need to think about with timing. One is that every instruction has a timing on it. Actually, the best place to look at that is instructions, right? This is number of clock cycles per instruction. So for instance, and the smallest possible time for an instruction is 2 clock cycles. You'll see a lot of clock cycles 2. These are all sort of immediate 0-page stuff. But then when you get up into doing absolute 16-bit addressing, then the timing takes a little longer. Here's one. It's 3 clock cycles, stuff like that. So right now we're just sort of running this thing literally in that loop as fast as it'll go. So this isn't super important of itself, and we won't see a big difference from keeping track of the timing. Although it could be interesting to see how fast the how fast the program runs and how many cycles we've gone through. So I think the plan is going to be to add, here, let's actually go. So today's plan. So 1, deal with instruction timing. So this is going to be including something like add a cycle counter temporary. I'll talk about that in a second. To the chip. Have each instruction increment timing based on its cycle. And for fun, we're just going to do time the program and see how fast it's actually running. The reason I'm going to do that is because we will be eventually the next part is going to be let me go implement true. So we're going to implement true cycle timing, dealing, and we'll talk about that in a little bit, but dealing with the like how long a cycle actually takes. So we'll need to use either thread sleep or spin sleep crate. We'll need to use batch up instructions based. So I'll go back up. I think that's a good overview of what we're going to do. There's probably more to it. So the deal is that we are going to be so this is the cycle counter is going to be temporary. The reason it's going to be temporary is because there's no actual like sort of state in the chip that knows what like cycle count it's on since the beginning of time. What we'll eventually have to do, so the to do here is pass like cycle ticks. So like every time it cycles, to riot and TIA. And then we'll also need to like sync past cycles to the sync the TIA color cycles. I'll show you a little bit more about that before we get started. Cycles to clock cycles, and there's a bunch of stuff that the TIA can do, like pausing the chip and stuff like that. So we need to take that into account. Cycles keep running even if the chip is paused from writing instructions. There's a good reason that these things get paused. Running. I'll just leave this open as bit of a waypoint. So so once we know how fast it's running, we'll know whether we need whether we can get away with thread sleep or spin sleep. Basically, thread sleep uses the operating system sleep, which is not particularly reliable. Spin sleep basically just runs at 100% CPU, and so I think the spin sleep crate does a mix of those depending on how long you're trying to sleep for, and it's supposedly more accurate. We'll do a little bit of benchmarking of that. I would love not to use spin sleep if we don't have to, but I think we can, and I think we can batch up instructions enough to make that happen. So let's take a quick look at what I mean by cycles here. So let's all right, so this is what I was talking about, clock counts, this color counts. So there are 228 per line, only 160 of those. So this is the number of times the cathode ray beam is able to change color, since it's drawing from, sorry, I'm pointing at it, it's drawing from left to right. This time is the time it takes to go from right to left, but as it moves across, it's always sort of drawing what the last thing it was until it changes color or on or off or whatever, and that's what the TIA is doing. It does that 228 times per line. 160 of those are actually when the beam is drawing, and then it does that 262 times over the course of the screen. Again, the overscan and vertical blank here are the time that it takes for the beam to go from the bottom corner up to the top again. So like I said, there's a 3-to-1 connection between color clock counts on the TIA and machine cycles on the 6502. You can see it's 3 here. It's not approximately 3, it's exactly 3. They are wired to be synchronized that way. So we can figure out the rate of, we can figure out the speed of the, what am I trying to say? We can figure out the speed of the processors by doing a little bit of math here. So let's go ahead and do that real quick. And we'll do this again when we come back. So we use, is it DC? Is this the one that I want? There's 2 calculators. No, that's not. So it's DB? BC? There, BC. Yeah, the DC is a stack-based counter, and BC is a more sort of standard calculator. So let's take a look at that math. All right. So let's talk about the one we care about most now, which is the CPU. I just hit the wrong button. 76 by 262. So 76 by 262. We can actually say our var. So that's actually not even quite there. So that's 19,000 per frame, right? So var. So we're gonna say roughly, although it's not quite correct, that happens 60 times per second. It's a little bit off. There's a great video I can pull up at some point if you would like to see that. And that gives us our clock count of 1 million, 1.2 megahertz, right? So if we want to figure out how long each clock cycle takes, we can just take the inverse of var. I'm saving this off because I'm going to use it. Oh, I need to set something. Then it needs to be, it's precision. I have spaced on how to do it. Well, that's what Google's for. BC precision. Linux BC. Scale. Scale is what I'm looking for. Scale is the answer. So scale. Let's go for something we'll never need, which is 20. So then var equals 1 over var. That's back to our inverse. You can see that's a very small number, so we can actually just do that. So times 1,000 is number of milliseconds, times another 1,000 is number of microseconds, times another 1,000 is the number of nanoseconds. So it's 837 nanoseconds per clock cycle, and if we multiply that by 2, our slowest instructions take 1.7-ish microseconds. So we'll need to take that into account going forward, but for now we're going to do the easy thing first, which is always fun. So what I need to do is remember how I set my Vim up to change windows. All right. So basically all of these instructions are going to need to increment a clock. So let's start with the clock on the chip mod.rs. And we're going to do that. This is going to be temp. Actually, I'll just say to do. Oh, interesting. I've never seen that highlighted before. Temp. Store the clock. And we may. I think we'll be fine to do this. Yeah, I'll just make that a pub cycles. And we'll make that a U64 just to make sure we don't run out of space in that. I'm just going to say it's not used. Did I spell it wrong up here? Yeah, I did. Cool. And then we're going to go back to our instructions. And basically for each instruction, this is going to be a little bit boring, but we'll get through it quickly. We're going to increment the count. Some of them are easier than others, so we may have to throw some to-dos in here depending on what happens. But after we do this, we're going to do chip dot cycles. And we're going to do equals plus equals 2. We're going to use that for a lot of them, so I'll just copy that. That's 2 cycles. This one's 4. This one's 3. This one's 4. This one's 4. I think we'll get to a more interesting one at some point. This one's 2. Whoa. Extra stuff there. So this is interesting, right? So this changes depending on what happens. Cross page boundaries is an interesting. Equal hex, so the width is 1. It's my width is. I don't think the width is actually 1 here. I think I transcribed that wrong. Let's see if we have a. Yeah, we copied it over. So let's take a look at our docs here. Length of 2 bytes. All branches are in relative mode. Blah, blah. If the branches, yeah, so these are all relative, so we'll have to see if we'll see what this looks like. Hold on. So this is actually. Oh, no, not that one. So, we're always going to up the typing by 2. If we take the branch, we're going to add 1. And then this other cycle comes from basically when we do this wrapping add to the program counter, right? Whether the top byte of this U16 is the same or not. So basically that looks like if we're going from 0x, so we go from 0, 1, 1, 1, just for fun. And then we break, and then it goes far enough that it changes. Let's say it goes down to 0, 0. This would never happen, but it's just a theoretical to F6, right? So the way that we can tell if it's crossed a page boundary is if it's gone, if this top byte here is different, because the pages are a byte large. It's a byte of bytes large, right? So it's 200. Each page is 256 bytes. Is that right? Yes. Okay. So basically, what we'll do is instead of just adding this straight to the PC, we'll just so we'll say let adder, and then basically if so if adder, yeah, so we'll just have to do a little binary math here. We'll mask it with, so we want that, we want to ignore the bottom part, and then we'll do a chip.pc. Same mask. And if that's true, we're going to add another cycle before jumping. What doesn't it like here? I can't see, so I may need to actually close this over here. Let's save it as Scratch. says it's not used. Is it? Am I shadowing something? It was just stuck. It was just left over. Okay, that makes sense. And so then instead of doing this, we're just going to jump to the adder. And if all goes right, we should, when we run it, get stuck in that infinite loop again. So we're going to map our comma t, which is our later, to write the current buffer, and then run cargo. And then I just undid that, but there it is. All right. Cool, so we didn't change anything in specific. And actually, if I switch over to our main... Oh, you know what? I need to keep going. So, I think that this is all kind of be the same. Here, this could definitely be abstracted later, but we will deal with that when it comes, because these are the same rules. Timing 2 plus 1 if taken, which is here, plus 1 if across page boundary, which is here. Okay. Oh, I missed the 2 cycles all the time. This timing is 2 all the time. Jump subroutine is 6 all the time. Return from the subroutine, 6 all the time. Exclusive OR is 2 all the time. Cool. So that's pretty straightforward. There's a lot more to do here. Definitely sort of keeping my eye out for abstractions as I go. So one thing I need to do, just because of the peculiarities of cross-term, is go back to my mod. Where was it? No, actually I need to go back to my instructions. Wait. I've gotten ahead of myself. What am I up to here? Memory map, right? And where I was returning this instruction that got us into the loop, I need to actually get rid of that. Because with cross-term, if I get into that infinite loop, it won't ever let me out. So before we start running it, let's go back to our main and print out here cycles. We don't need that to be an X, we just need that to be that, and it'll be chip dot cycles, and we'll put a divider here, and I'll show you what I'm doing in just a second. Cargo around. So I'm running this in debug mode so you can see all the instructions. You can see our cycles number is counting up as we go, which is what we would expect. And it turns out before we get 2782 cycles before we panic with an unknown instruction. So that would be a good place to commit. And then we're going to take a look at how long that takes to run. The debug mode runs slower because it's printing to the screen, and we want to be able to see stuff. So I've intentionally made that a little bit slower. Add. Yeah, we're going to add all of this. Yep. Oh, I did those wrong. I should have tested them. I've been trying to get away without testing some certain things that I'm pretty sure of, because I'm going to be moving stuff around a lot, but I just did something very wrong. I'm glad I caught it. I am a big tester, but like early days in personal projects that are like really loose and I'm learning from, I don't tend to test very much. So what happened here... So we want to add one if those are not equal, not if they are equal. The good thing is that we repeated the exact same thing here. So we should be able to change it there. Stat. So we're going to say added cycle count to the CPU for testing execution speed. And then we also increment cycle count. We'll push that. Well, apparently I can't type. Hold on. Slow down. There we go. I try and go too fast when I'm typing out that long passphrase, and that's what happens sometimes when I'm ahead of myself. All right. So actually, let's take a 5-minute break. I'm going to go use the restroom, top up my water, and I will be back to implement timing, which will be fun. All right, I am back. We are going to talk about... Whoop, I'm trying to get the volume of this right in my head. We're going to talk about timing, which is super fun stuff. So let's do a little bit of timing of what we have so far. So we'll use... I might need to pull up the docs. In fact, I'm just going to go ahead and do that. Standard library. So the thing we're interested in here is instant, I believe. All right. Yeah, so non-decreasing clock. Opaqueous with blah blah blah. It's all fine. Yeah, so we can get sort of elapsed time from the time we made an instance. Maybe. Oh, interesting. Cool. So we'll just have to be careful about not making it panic, because we will be using instance here. Yeah, this is talking about, for example, the following snippet. Something about the underlying system call. That's just fine. Okay, cool. So we don't have anything started, so let's go to main. We are going to use, we got standard, and that was standard time instant, and we'll need probably duration as well. Yeah, well, maybe not. Let's see what happens. Okay, so we've got that in scope. Okay, unused, yep. Makes sense. So where's our loop? Cool. So basically, at the beginning of, like, before our loop, we're going to do let. Does it need to be, let's see, does it need to be immutable? No. And now equals instant. New, I believe. Now. Semicolon, of course. And it's saying now is not used. And so then we're going to panic out and we find an instruction that we don't know. But before we panic, let's do the following. Let's see. We're going to do time instant, or we're going to do now dot elapsed, do it as nanos, I believe the call is, and we'll have to do some math to get that. This is saying unreachable code. That's right, because you need a closing. As nanos. We'll add that to my local dictionary so it doesn't bother me. So we'll see how long it takes to run this loop. That's the first thing we'll do. Actually, I'll just do it in awesome. Time is 23.401 nanoseconds, so 23 microseconds. How's it going, Togglebit? Audio level's very low. Like, in general. Thank you for showing up and letting me know. Unsure what to do here. I'm almost peaking. Well, I'm not peaking, but I'm... Let me see if I can... You still around, Togglebit? I may need help debugging that. Do you know anything that I can do? Because like the mixer on like the audio mixer on OBS is showing that like my voice is climbing towards like the yellow. Yeah, right. Yeah. So the mic is climbing towards yellow and the music is sort of in the lower end of the greens. which is why I'm a little surprised that the audio seems low. Can't even hear music. Okay. Wild. I wonder if I have my music set up. Can you hear the music now? How is it compared to my voice? Because OBS is showing it being about the same level as my voice. Can't hear the mic at all. Maybe it's got the wrong mic or something. Hold on. No. Why don't I just bump the mic audio and we'll see. Oh yeah, actually I probably can. Let me move that around. Here, we'll put that up 20. Hold on. Let's see if it sounds crazy. How is it now? Much better. I just bumped the volume up in OBS. It's like showing me as like peaking out like real hard, but I'm just not gonna worry about it. I don't know why it was so off from what it said it was. It's weird. Okay. How'd your stream go this morning though, Togglebit? I didn't catch it. Child care was happening, so. Oh, red, like it's like making the whole bar red. I don't really understand. Wow, you're already at alpha release. That's awesome. It's funny because I can't always keep track of like sort of where you are in your own roadmap at any given time. So I'm like, yeah, that's exciting. Yeah, so I was actually, what did I do? Oh yeah, I implemented sort of chip cycles, and basically right now I'm seeing how fast what am I saying? How fast I run all these instructions at, so I can like have an idea of how many I can batch together and like how fine grained my like sleep needs to be. I'm trying to see if I can rely on OS sleep rather than like spin sleep or something like that. And I think it'll be fine because I really only need like if I can run them all the instructions fast enough, it's fine for me to just kind of run them all at once, and then every frame, every 60th of a second, like update the screen. So I'm not super worried about it, but I'm just really curious where I'm at right now. Oh yeah. So we looked at the time. Now we need to know cycles. What we're gonna do. guess I'm just going to do it here so I can use it. I, for some reason, cannot spell cycles today. I can't spell anything, is what it comes down to. Yeah, the second C is just escaping me. I don't know why. Waiting for a lock file on build directory. File lock on build directory. Oh no. Oh well, thanks for hanging out. You're one of a couple at this point. I'm sorry you're having a headache though. That sucks. Yeah, I actually kind of like streaming on the. There it goes. All right, so we had 25, 26 cycles in total in 22, 23-ish microseconds. So if we use our calculator to 526. Does that seem right? Wait. So it's taking about 8 nanoseconds to run each instruction, or well, each cycle. So each instruction is taking about 16, and the number of nanoseconds we need is like 850. So we are running 100x the speed of the actual processor, which makes sense. I'm guessing if we were in release mode, we'd be running even faster. So we will need to synchronize that. And let me think about exactly how to do that. I've had this on my mind for about a week, and I'm still sort of sussing it out. I think this might be something where I want to test drive my solution and then pull it in. Let's see. I'm too scared to use my tablet on stream. I need to practice off stream. Actually, you know what? I'm not scared. It's easy. I got it fixed. So I can probably do this just fine. All right. So I'm going to see if I can think through how I'm going to do this. Okay. So I have... Will I be able to draw something that makes sense? So I want... I might not be able to draw something that makes sense. I might think this out in code instead. This is me going back and forth on how to do this. Tend to get... Yeah. Yeah, I guess with Rust Analyzer, that makes sense, because it was probably just running... still running from when I backgrounded the code, or backgrounded the Vim. Ooh, all right. Breaths. Okay. So again, I think it's gonna live out here in main for now, and then I'm gonna put it away. But basically, I think the idea we'll do mod tests. I do need to get myself a snippet for tests. Because I don't remember the magic incantations all the time. That's it. I have tests somewhere else. I'll just steal it. Oh, nice. Yeah, I might do that at some point. I was feeling like a pretty chill weekend stream. Yeah, I tend to get like about one or two people in and out for the weekends, and then if I do it during the weekdays, I get like seven or eight or sometimes more when I get a raid from somebody, for whatever reason. I guess just my crowd is available on the weekdays or people are avoiding work or whatever. Um, but I'm sort of keeping all this stuff for posterity and putting it up to YouTube. So yeah, but thanks for the advice on promoting my stream there. I might do that when I have something super interesting I want to like promote, like maybe when I add graphics or something. That might be a good idea. So let's steal. So I had it right. So then I'll make a test. What am I gonna do? I'm gonna do. So I think I'm gonna make like a separate kind of set of functionality for this. So I want to. I haven't, yeah. So for graphics, I haven't even thought about it yet. I'm not even. Is macro quad like a? Actually, let's take a look. Because I'm all for thinking about it now. I was thinking about. Oh, it's a game engine. Might be nice. I was thinking about just like using SDL2 or something like that. Those bindings are pretty good. If there's something like easier, the thing is like the graphics are like going to be like fun when they show up because we'll be like seeing things on screen, but like it's kind of just going to be, actually this is a good situation to use my pad here because of how the screen works. Like there's going to be like there's going to be like lines. Whoa, yeah, I'm really good at I should put that on the table. So there's like going to be lines of on the screen. Gosh, man, yeah, that's me not being able to draw. But basically, like, we're good. Like, it's going to change the color like X number of times, like based on some state. And so all I need to be able to do is like draw essentially a series of, and then on the Atari, like the width of a pixel is like significantly wider than the height. The height is just a scan line, so it sort of looks like this over and over again. And so I need to be able to draw like little rectangles, sort of like that, based on like sort of the state of the state of like the emulated hardware, and then that's it, right? Like that's kind of all. That's all she wrote. It might be nice. We'll see. I think I might try and keep debugging in. Yeah, this is a great picture, by the way. I might keep debugging in the console. I know that some of the other Atari 2600 emulators use like a graphical like version of the debugger, but I feel like with a nice terminal user interface setup that. Like I think you could do all that and not have the overhead of like trying to figure out all the different ways, like all the controls on all the different platforms and stuff like that. So that is my goal. Let's see. I don't know what to name this test, so we're just gonna say like it does something. I'm not even sure what does it. Okay, so basically the idea, I think I'm just better in comments. The idea is I want to bundle up a bunch of... Actually, what I can do is a little bit of testing here. Like, not of my code, but like of the sort of system and see what I can get. So I want to do use standard time duration, I think it is. What the... it needs double colons. Double colons. Double colons. There we go. It doesn't like that I've... Yeah, it doesn't like that I've done it, but it's still there. I don't really care what it says. So I'm gonna do let now. I'm gonna use instant too. So I'm just gonna check and see how long or what kind of reliable intervals I can get with sleeping. So basically, I'm just going to do this in a test, and it really doesn't like how I'm doing this, but for me, that's the easiest way to run it. And check this out. So we're going to do... And we'll do... We need standard... Where's thread? Sleep. Thread sleep. Yeah, it's just in thread. Oh man, do I have caps lock on or something? Standard thread sleep. Cool, so we'll sleep. From nanos, I believe it's called, and we'll just do something close to what we know we want, which is 870-ish. That'll be fine. And then we'll do let. Oh, you know what? I can't do this in the test because I don't think I could print in the test. We're going to do this the old-fashioned way. Hold on. Let me pull this stuff out. I have really... There we go. We're going to make a new main. There's probably a better way to do this. Remove the whole use item. It's not like there. It's not like... Oh, it just doesn't... This is wrong. I somehow made everything lowercase. So we're going to get our instant from to sleep for duration from nanos, and we'll do something like I said, we'll do something close to what we're looking for. We'll just do 900 for fun. Then we'll actual. As nanos. It says I don't need... Oh, because I have it up higher, I guess. Which is fine. Functions never used, that's fine. So cargo, run that. So, yeah, so I tried to sleep for 900 nanoseconds, and it actually slept for something like 92,000 nanoseconds. So it's 2 orders of magnitude off. Let's actually see if that's... And it's really inconsistent. That was a very long time. I'm not... What doesn't it... You want me to print the... Oh, really? Okay. Seems the same in this situation, but I did do as nanos. Let's... So maybe I can just do elapsed without that. Let's see what it says. Oh, yeah. That is nicer output. Thank you, Togglebit. Yeah, I'm getting anywhere from like... So it's not great. And sometimes I'm getting a very long time. Just like 2 orders of magnitude off. Let's take a look at that at what sleep... What is it called? Spin, sleep, rest. See if that gets anything more consistent. It's on 111. Okay. Spin underscore sleep. What is the cargo package? Or the crates IO package? Is that doing something like yielding the thread in a loop while checking the elapsed time? In this case, I think we're... I mean, unless I'm mistaken on how that works, I think we're actually just... Because I today, like, wrote my own main. I'm really just, like, sleeping for 900 nanoseconds and seeing, like, what I get back, which is like 2 orders of magnitude off on a good day. It could be that I don't fully understand how this stuff works, which is like definitely a real thing. I haven't done much with this kind of stuff. Spin sleep. Spin underscore sleep. Me either. Looking at the code, and it seems to be doing a lot more than that, so that's good. Oh, yeah. Oh, spin sleep. What's spin sleep doing? Yeah, no, I'm sorry. That I was confused as to what you were asking about. Spin sleep is apparently it uses the operating system version of sleep unless it like is unreliable, and then it'll like basically, I don't know how it does this magic, but basically it sort of spins in a busy loop, which eats up processor a little bit, but like is also like not. It's also pretty reliable, so we'll see what happens. So let's see, where are we? So instead of this, we'll use spin sleep. I hope it's called sleep. Okay, so that's actually like wildly inaccurate too. Maybe that first one was. It seems like that first load up was. So this is. It's definitely a lot longer. It's like not quite an order of magnitude, but it's like twice as long. I feel like this is going to be a lot more easy to deal with. So let's say. Let me do my BC again. So it's 76 clock cycles times 62 lines times 60 frames per second. So 1 over all of that. I need, what is it called? I keep forgetting what it's called. Yeah, I just need to leave this up. Scale. For some reason, scale has like completely left my brain. So scale. 20. Alright, so that's time. This is millis, micros, nanos. All right, so 837. So let's see. If we bundle up 10 cycles, yeah, so if we bundle up 10 cycles here, we can get to 8 microseconds, but we were still. Let's see what happens if we do our test with 8 microseconds. Or we'll go. It's fine. So that's actually really close. So I feel like we could safely probably bundle 10 of them. They happen super fast from our one test. And then... yeah, and then we'll just do our calculations based on that. This will be an interesting thing. I've thought a lot about this, but I've never quite figured out how to make this work. I need to run and use the restroom. I'm going to take a 5-minute break. I'll be right back. My fingers just do not want to type today for whatever reason. Alright, I am back, and I'm trying to think about how to implement this timing thing. So we actually let's go back. We'll go to BC. We'll save this out. Let's get sale equals like 20, and then we're doing 76 times 262 times 60. I've done this a million times, but that's fine. 1 over all this times 1,000 times for millis, 1,000 for micros, 1,000 for nanos. Let's say 837 is our number. Cool. So let's scratch. So we're here. Let's put 837 nanos per cycle. Now I'm trying to think of how I can test this. I'd like to abstract this so I'm not just doing it like sticking it into the loop. I think I can do that pretty easily. Might just be a function or something. Let's see. So the idea that I want here, we'll uncomment all this. Super, let's use everything from super for now. Get rid of this. So, what's the smallest piece of this I can do? Let's do some comments before I write a test. Alright, so I think the thing I want to do is say we have a start of some sort, and then we run some stuff. It doesn't really matter what it is. And then we check. So what's it now? Let's say elapsed. So we have elapsed time from now. And then we have how long it should have taken. So we're gonna try and sleep for should have taken minus elapsed. And then we have some interesting stuff because I think that sleep is guaranteed to never return early, but because it's even spin sleep can return a little bit later, right? So I think we have to do something like start. So this is like a new loop here. This is where I got stuck with my last emulator. Camera is frozen. This happens in OBS all the time. I don't know that I can do anything about it without restarting. I've looked it up and I can't figure out what's happening. Let me see if unplugging it and plugging it back in works. Thank you for letting me know. Make sure I have the right thing here. Yeah, do not know what to do about that. One more second. I'm going to try and add another camera. To see if I like. It's frozen again. Yeah, I don't really love this camera. It's I don't know how to like do anything with it. I might get a new one at some point, but what is MPV? Is that a like alternate streaming platform or something? But too close up to be a. Yeah, it's not a GoPro. I don't know what. To M player, huh? Hold on, let me remove this. Because that one froze too. I don't know. Yeah. Oh, okay. That's a good idea. Oh boy. Well, I have. I'm trying to decide whether I'm just going to keep going without the camera for now. I would really love to get some progress on this, but my kid's also up, so I may call this one a day and just wanted to get more done here. I'll see if I can't make a little progress in just a few minutes. I just really want. Okay. So new. Yeah, I'll deal with the webcam later. I don't know why it keeps doing that. Test. PV. Yeah, I'll deal with that at some point. Okay, so where was I? So we run some stuff, we have elapsed time, sleep for what it should have taken minus elapsed. So then we want to say like, so we have like when we should have woken up, and then like when we did wake up. I do believe I can continue to use that instant for a while, although I don't know if you like are able to reset it or not. Do I have to new up a new one? It's like everything kind of messed up. Like this used to be in dark mode. Don't know what happened. Now duration since earlier instant. I mean, I might as well just use new ones, I guess. Yeah, I'll just use new ones. Okay. So we should have woken up. So then what we want to do, let me see. So we run some stuff. There's an elapsed time. We sleep for an amount of time that's what should have taken minus whatever it has taken so far. And then when we wake up, so we're going to have like a total amount of time. So we start with like a... So then we'll need to subtract this from the next sleep, right? That's that difference. So then we start all over again, but then we have, so it's like taken minus elapsed minus like run over, basically, right? So so before start we like calculate. Run over is not really a word, but we'll go with it. Calculate run over. Start, run some stuff, elapsed time. Let's see if we can actually just like do this in a test. So I feel like this might be tough to test this way because like I'd need to like mess with durations and like mocking stuff out. So maybe there's some really smart stuff you can do with tests and durations. Let's see if anybody on the internet has done anything super smart. Rust testing with instance and durations. I don't want to get into mocking stuff. So how can I decouple this logic from come back to testing. Let me just, now that I have this idea, let me see if I can sort of make it work and then think about testing later. I think that I can probably do it without like mocking anything in particular. I think I might be able to do it by like running a bunch of like instructions and then like making sure that the time is like that it took to run them is within some like realistic thing. So we're gonna like, yeah. Little cowboy coding here. So we have now, and I think we're gonna want to do this. We'll just gonna do this in a really imperative way. We'll call this run over. We'll just 0 for now. And it doesn't know what the... Okay. And this will need to be mutable because we'll need to update it every time. We can start with a mutable instance of now. Timing stuff. Okay, so we won't worry about debug yet. In fact, we may need to do this when it's not debug. That'll be an interesting thing. All right, so if we're gonna bundle 10 of these together, that actually makes things super interesting. Yeah. When in doubt, do it ugly. So let number cycles run. If equal to 10, rest format, stub it. All right, so if we've run 10 cycles, then we need to sleep for whatever we have elapsed. And actually, let's make this a duration from nanos 0. We'll need that duration. Instant. So then, before we go, so we're gonna do we have sleep? That's the question. Cool, so we're gonna use spin sleep. So we need cycle time equals cycles run. So that duration from nanos cycles run. That's times our number that we got earlier. And our scratch buffer, which is 837. So that's the total time we should take, right? So we're gonna do a cycle time minus whatever duration that is, minus run over. Right, so then we're gonna do So we need. All right, we're actually going to reuse this now variable. So minus. To see how long we slept. We should probably calculate. Should sleep. Should sleep. And we'll need to set a new, so now equals so that's our new now, and then we can say run over var is equal to now so whatever time actually happened minus should sleep. Then we're going to set up this instant again. Okay, so it's pretty dirty, but basically we're saying here's how many we've run a bunch of cycles. Well, this is how long it should take. We're setting up a new, or we're getting the elapsed time that we should have had, and then we are saying we should sleep the cycle time, so like how much like time that should take, minus whatever we've already taken to calculate these things, minus the whatever run over there was from last cycle. In the first case, it's 0, but we see we're setting it here. When we sleep, we just check out the difference. I'm sure there are some edge cases here, and then we reset this instance so that we can get our elapsed time next time. So the only thing left to do is to check the cycles run. So currently we're going by the, so we're gonna do some more gross stuff. Let current cycles equals 0. If, so we may be able to clean this up. So if chip.cycles minus cycles is greater than 10, so we do that. And then we set previous, some pretty imperative stuff here, which is fine. It's whatever the number of total chip cycles is. So I think it's kind of all we need, and all of our sort of so clean this up. This definitely needs some work. I think it should definitely be tested. There's some edge cases like, what if it takes like a whole lot longer? Will this still work? Like if it takes like double what it should? But I think we're like not too far from something that works, and then we can. Overflow when subtracting durations. Cool. Time.rs. I think that was probably it, but we'll see. Shit. Cycles minus previous cycles. Spell cycles right. Delete. Run. Don't need that. Okay, so subtracting durations. Let's see. So I'm guessing that's here or here. So let's just spam our. Cycle time. I'm not talking because I'm. And then let's see what the run over is. It could be here too, although that would be surprising to me since we're replacing that. Let's take a look at should sleep. I don't think we're getting that far, but if we do. Waiting on a lock. Rest analyzer, why are you doing this to me? Yeah, so these should sleeps actually look about right. Everything looks about right. So what is it saying? So in one case we... Cycle time 9. Let's make our lives easier and print. Actually, we'll just do it after here. We'll do it before here. We'll print a new line. Because that last one's... We'll print a couple of them. Right. Have to figure that out. It's being a little too fast there. So we have an elapsed time of 274 nanoseconds. The cycle should take 10.044 microseconds. The runover is 22. Okay, so this is what happens, I think. This is the edge case I was talking about, which was I didn't think would actually happen. When the runover is bigger than the... Can you not have a negative duration? Probably not, right? Got into a weird state there, but... Oh man, I managed to go to a different screen entirely. Duration. Check to add. So you can't have a negative duration. That doesn't make sense. Okay, so that is actually the edge case we were talking about if there's like a really long sleep. So I think maybe the solution right now is to bump our number of cycles run to like 100. Since apparently we can sleep, we can have... Yeah, okay. If we still get this, then what we can do, I think, is... Yeah, if our should sleep would be negative, so we'll check that option, then we'll do a little bit of math. And have to do some catch up. So that's where it's sort of testing all this up and test. Because I think we want to get a little more granular than 100 cycles, but we'll see. Cool, so the time there was 2047, that's in nanos, right? All right, we're like, yeah, okay, so we're doing double duty with now, so we actually need like let total time equals instant. We're gonna have a couple instants around. This is just temporary for debugging, but I think we may have done it. So total time, and then here, instead of doing now dot elapsed, we're doing total time elapsed as nanos. Waiting for Rest Analyzer, give it a second to catch up with me. Okay, so the time is 2 milliseconds. So let's actually do the math there. This is scale. We'll do 20, and then we'll do 205, so 51691 divided by 2526, which is about what we were looking for. I think that we have a bit of an issue. It's not quite as long as we would like because it should be 834, I think we have a bit of an issue with this last set. We're not sleeping. It doesn't really matter because it'll keep going. I'm curious. Cases. So we're going to handle cases where the sleep took a lot longer than it should. So what happens if we drop this down to 10 overflowed? Let's see if 20 overflows. Just doing some guess and check. Rust analyzer. Okay, so that overflows. 40. Okay, and then I'm hoping that we get something closer to what we expect. So scale equals 20. And then we're going to do 1, 2, 1, 1, 8, 7, 3, 0. We could actually just put this in our divided by 25, 26 cycles. Yeah, that gets us a lot closer to our sort of normal time. I don't think we have to handle that because it would keep running, but we actually have timing. This is pretty rough, but I'm going to leave it at this, and then maybe if this is interesting enough, do a refactor on stream. I think that I'm going to do some more implementing stuff off screen. I think that we're getting to the point where we need to implement the riot and the TIA, and when we implement the TIA, we're just going to hook it up to graphics. Maybe something temporary. But we might even be able to play it in the terminal. I'm not sure how. It's like 80 to there. I'm not sure we can quite do that. It needs to be like 160 wide. Yeah. And then something out tall. Okay, cool. So let's add that. We have implemented timing. We did it. Oh, that was a little rough, and I have to figure out my webcam and all that stuff, but that is about it. We only have a couple people, including me, to raid, but let me see if there's somebody I would like to raid to. Anybody I know online? Anybody doing anything cool? Somebody's doing the C compiler for the CPU thing. Let's see. Let's see if anybody's doing any Rust. Nope, everybody's doing Rust. So let's go hang out with this guy who's doing a C compiler for his CPU. Hero Dev is his name, so